Welcome to LIB Academy. In this video, I'm going to take you through inverse Laplace transform problems. And by the end of this video, you are going to see some of the easiest ways to evaluate inverse Laplace transforms. And what exactly are inverse Laplace transforms? When it comes to inverse Laplace transforms, it is somehow tedious if we don't know as which way to grab the question. And there is a need for us to know, all the elementary Laplace transforms so that we will be able to do inverse Laplace transforms with ease. Well, back to the idea of Laplace transformation, we say we have a function that is difficult to work with and we are transforming it to a function that is easy to work with. So let's say we have a function e of t, e to the power at, and we want to work with. It is very difficult sometimes, assuming yes, this is a tedious function to work with. So we convert it to a function, to another function which is easy to work with, right? So when we are done, there is a need for us to convert our function back to its original state. So the Laplace transform of e to the power at is this. So the inverse Laplace transform, which we are converting this to this, to give us e to the power at. I hope that is clear. The inverse means we are converting this back to its original state. And it is denoted by inverse Laplace transform of this. So these are the elementary Laplace transform. Laplace transform of any constant k equals that constant over s, e to the power at, 1 over s minus a, sine s at equal a over s squared plus a squared. There is a need for us to know these very well so that we'll be able to do inverse Laplace transforms with ease. But I'll try my best to give you some shortcuts to work with in this video. So find the Laplace inverse of this 3 over 2 s to the power 4. So the first thing you need to know is to look at the question very well and what function it is of which function form. Is it e to the power at, sine at, or cos at, sine hat, or those stuff. So that is why there is a need to know the basic Laplace transforms. So you could see that this function is of the form t to the power n equal n factorial of s to the power n plus 1. Can you see that? Okay. Since this function is of the form t to the power n equal n factorial over s to the power n plus 1, therefore I can see that this function, I can write it in this form. Let's say still I don't know my n. Let me write the denominator first. So s to the power 3 plus 1. Since mostly n is going to be increased by 1, so n plus 1, I can write this power 4 in the form of 3 plus 1. So now we are analyzing the problem. So you could see that comparing this to where the function is coming from, I have to get 3 factorial here, right? 3 factorial. So if I'm to go further, this means that 3 factorial is 3 by 2 by 1, which is same as 6 all over s to the power 3 plus 1, right? This means that in the original function, the function that is given to me is supposed to be 6 over s to the power 3 plus 1. But now that I'm having 3, that is why there is a need for us to analyze the problem very well before taking the inverse Laplace transform straightforward. Because there might be a constant that is multiplying through, and that one will also contribute to the actual result, this. So now what I will say is that I now have a true numerator and a fake denominator. So I have to work that out. for my denominator, I now have a true numerator and a fake numerator. For the denominator, everything is okay. So I would like to ask myself, my denominator is supposed to be 6, but now that it is 3, it means that something was multiplied by 6. That is why I'm getting 3 here, right? So I don't know that thing. So I can just go ahead and say something was multiplied by my true denominator and it's giving me a fake denominator. That is how I put it for easier understanding. So something, let me call that thing y equal fake denominator. So something was multiplied by this, giving me that. So solving this, I'll get that something, which is y to be 1 on 2, 3 here, 1, 3 here, 2, right? So now let's come back to the problem. After we are done analyzing the problem, the Laplace inverse of 3 on s to the power 4 can be the same as Laplace inverse of, I have this one. This is a constant. Remember, what will change the value of our original numerator is mostly a constant. So let's bring that our constant have Laplace transform of 6 on s to the power 4. I hope this is clear, because looking at this, if half should multiply through this, 2 goes here, 1, 2 goes here, 3. So at the end of the day, we are going to get 3 over s to the power 4, which is the same as this. Sometimes you can analyze it and see the constant straightforward, but mostly if you are not good at guessing, you can follow this procedure. So now that this is a constant or a coefficient, I can bring it out and take the Laplace inverse of 6 on s to the power 4. And already I know that this 6, because I wanted to analyze it very well, that's why I evaluated it. It was 3 factorial, right? And that is my n, right? Comparing to the problem, that is my n. Or you can get your n value here, 3 plus 1, that is your n. So now that the reason why we are doing this to see whether there was a constant, right? And indeed there was a constant. That is why when we got here, instead of this place to be 6, it is 3. Instead of this place to be 6, it is 3. So now we know the value for our n. To convert this back to this form, we just write 2 to the power n. And our n here is what? 3, right? Comparing it here, our n here is what? 3. So this is just simple t to the power 3. But we have a constant, so just multiply through by that constant. So this is the Laplace inverse of 3 on s to the power 4. Let's take another example. Find the Laplace inverse of 6 over s to the power 3. So first of all, I have to check the question very well and see which function is of this form. Definitely is t to the power n function, right? T to the power n function, which is n factorial over s to the power n plus 1. If you want to know, mostly it is t to the power n function. You could see that the exponent of s here is somehow 2 or more than 2. When it's more than 2, that is a big hint that it is t to the power n function. So now that I know this is the function is of this form, let me start my analysis. So analyzing this very well, so 6 over s to the power 3. First of all, just do the denominator analysis first. The denominator is going to give you an n value first. Quickly. So let's say my denominator here should be n plus 1. I can write it 2 plus 1 since it is 3, right? So 2 plus 1. So this is clearly telling me that my n is 2. So if my n is 2, the numerator should be 2 factorial, right? Should be 2 factorial. And 2 factorial is the same as what? 2, right? So 2 factorial is the same as 2 times 1, which is 2. So 2 out of s to the power 2 plus 1. So in actual sense, it's supposed to be the Laplace inverse of this function. But now that my numerator is not the same as the numerator in the given problem, I have to also work that out before I can take the inverse Laplace transform. Mind you, we have to do this to know whether there was a constant involved, right? So first of all, you do denominator analysis. When you are done, you do numerator analysis. So we are done with denominator analysis, and now we are numerator analysis. And like I said earlier, it means that something was multiplied by a true numerator to give you a fake numerator, right? So 2x, something multiplied by my true numerator. My true numerator here is 2. So let's say call that thing to be y to give me a fake numerator, which is 6. So evaluating this, I'm going to get 3, right? You can see straightforward that 3 by 2 is going to give us 6. But if you're not good at guessing, you can go it by it this way. So now that I'm done with my numerator analysis and my denominator analysis, so it means that Laplace inverse of 6 over s to the power 3 is the same as, and mind you, what will multiply your true numerator to give you a fake numerator is mostly a constant, right? And gotten that one to be 3. So 3 and for constant is equal to Laplace inverse of 3 multiplied by what? 2 factorial, which you can just write 2 over s to the power 3, right? So since this one is a constant, you can bring it out here. Laplace inverse of 2 over s to the power 3, right? So now that we are here, we're able to figure our constant out. Indeed, there was a constant multiplying the term. So now we know that Laplace inverse of a function of this form, t to the power n equal n factorial over s to the power n plus 1, is just t to the power. If we are converting it back, it's here 2 to the power n. And we know our n to be 2, right? Right here. Our n is 2, right? So t to the power 2. And because we have a constant 2 multiplying, we have a constant in the term, so just multiply that constant by your final answer. So let's take our final example on this. First of all, figure out where is the function coming from. Like I told you earlier, since the exponent of s is more than 2 going, that is a clear hint. Either it can be 2 or 2 going, right? More than 2. This is a clear hint that this function is a t to the power n function. We call n factorial over s to the power n plus 1. And if I compare this, firstly, I do denominator analysis. So denominator analysis. My s is to the power 4. So I just have to write 3 plus 1. It gives me 4, right? Yeah, 3 plus 1 gives me 4. So now I'm done with my denominator analysis. And this denominator is clearly telling me the value for n, which is what? 3. But I just want to go ahead and do my numerator analysis. Maybe I might have a false numerator, right? So if n is 3, I have to get the numerator to be 3 factorial, right? So 3 factorial 2 is 3 by 2 by 1, which is giving me 6. Indeed, this numerator here is a fake numerator. So I know that going forward, this one is just 6. So 6 all on s to the power, let me write 4 because we figured out our n. So 4, right? Now, I'm not getting 8 here because there was something happening. There was a constant. There is a constant working on this to give me that. So now, like I said earlier, this is my true numerator. So something was multiplied by my true numerator to give me a fake numerator. So let's call that thing y. So 6 by my true numerator give me a fake 1. So dividing 2 by 6, I'm going to get 3 goes here, 4. 2 goes here, 4, 2 goes here, 3, right? Yeah, so now I was able to get my constant. So first of all, do denominator analysis for problem of this sort. When you are done, check your numerator, whether it is okay. When it is not okay, you have to work on it. Then that will lead you to getting a constant. So now the Laplace inverse of 8, Laplace inverse of 8 on s to the power 4 can be written as Laplace inverse the constant 4 on 3. Now you are not writing it, you have to write this because you found a constant that is multiplying through this to give you 8 over s to the power 4. So it is indeed true. If we multiply this by this, you'll be getting this, right? So 3 goes here 1, 3 go here 2. So 2 by 4 gives you 8 over s to the power 4. So now you can go ahead and take your Laplace inverse, right? Because this is a constant, we can just bring it out. A constant or coefficient will bring it out, right? Laplace inverse of 6 over s to the power 4. So we know that the formula that corresponds to this, in Laplace inverse, our interest is to convert this back to this, right? And what we need is just our t value. And from our for our t value, we know it just right at the beginning that our n here, for our n value, we just know that right here, it was what, 3. So we just write t to the power n, which is 3. And because we have a constant here, just bring the constant 4 on 3. So that's it. So most of the time, you have to take your time to figure out the constant. Else, you choose you are likely to choose a wrong answer if we are dealing with multiple choice questions. So first of all, problems of this sort, do your denominator analysis, do your numerator analysis to find constant. If your numerator here, assuming here, if we've gotten here to be 8, which means our numerator is just the same, then we have no problem. But this is the case, we have 6 here and we have 8 here. It means we have to work it out. There was a constant. So, and that is what I will say that my true denominator multiplied by something to give me my fake my fake numerator. Sorry if I'm confusing it. Numerator and denominator. So that's it. So I'm taking it once again. First of all, you have to do your numerator analysis, or after you know where the problem is coming from, then you do numerator analysis. And then doing numerator analysis here, we've gotten to know our n value, and we got to realize that our numerator is okay, right? Our denominator is okay, right? And after we are done with the denominator analysis, we will see that our numerator is not all right, right? Because we are not getting 8 here. So we have to do something to fix that. And we know that our true numerator was multiplied by something. That is why we are getting 8 here. So we don't know that thing. So our true numerator multiplied by something to give us our fake numerator. So working that out gives us a constant of 4 and 3. So therefore bring that constant, and then this term right here, and we know that value for our n back here is 3, or you can just figure it out here as far as you know that the function is coming from this place. So knowing your n value and your constant, let's go ahead. Since we are converting this back to this form, you know n is 3 over, and then you multiply the term by your constant right here. Or find the inverse Laplace transform of 1 over s squared plus 9, right? And so far, the problems that we are dealing with, you could see that from the denominator, we have mostly we have s squared terms, right? we don't have S term. Okay, so this is tell you that we don't have any shift. We were dealing with shift problems later, so you will get to know that. So first of all, I want to know where my problem is coming from, right? So looking at the elementary Laplace transforms, we have sine 80, right? We have sine 80. For sine 80, we have e over s squared plus a squared. For sine h 80, we have minus between s squared and a squared. You have to consider all those stuff. And for cos 80, we have s as a numerator and s squared plus a squared, right, as a denominator. And for cos, you could see that we also have minus here. So looking at where your problem is coming from, consider the numerator and the denominator. So looking at this problem here, can I say it's coming from cos? No, because cos, we have s term at the numerator side. And for sine, it is only sine term that we have a at the numerator side. So this is probably coming from, for this problem, this is probably coming from sine function. And is it sine h or sine 80? Well, looking at the denominator, because we have plus there, so it is sine 80. That is where we have plus. We don't have minus, right? So good. So it means that this problem is coming from sine 80. That is why there is a need to know all these elementary problems. Formulas. So now, let's continue. So this is to tell you that if you have a problem like this, check the numerator and the denominator. Whether you have s component at the numerator and the denominator too, is it a down, is it plus or minus, and that will tell you whether it's a sine function or cos function. And if it is a sine or cos, is it cos h80 or sine h80? Is it a cos h80 or cos 80 or sine 80 or sine h80? Good, let's continue. So clearly, there is a hint that this problem is from sine 80 equal e over s squared plus e squared, right? So now, let me start analyzing my denominator. Analyzing the denominator first before the numerator is very sweet. So it means that I can read out this whole problem like this. I'm focusing on the denominator, s squared plus 3 squared, because 3 squared gives me 9, right? So now looking at I'm done analyzing my denominator. Looking at the original elementary equation, sine 80 equation or formula, I'm supposed to get a here, since you could see that this is my a, right? This is my a. My a is 3. So I'm supposed to get a here, right? Good. It's tedious, but just relax and follow. I don't know whether you might find it easy to. So now this brings in our true denominator, our true numerator and our fake numerator analysis. So I'm supposed to get 3 on s squared plus 3 squared, right? So this is supposed to be my true numerator, and this is my fake numerator. So it means that something was multiplied by my true numerator to give me a fake numerator. So let me call that thing y equal 1. So solving for y, you could see that y equal 1 on 3. So this therefore becomes my constant. Once you see that your true numerator, your supposed numerator, is not the same as what is in the question given, then you should know that there is a constant that was multiplied by this. So this is how to look out for the constant. And this is my method. You might not find it anywhere. So now I'm done with my numerator analysis and my denominator analysis. So it means that the Laplace inverse of 1 over s squared plus 9 equal the Laplace inverse. I found a constant, right? So let me write the constant. Mostly you can bring the constant out. It doesn't matter. After that, we are going to do that. Inverse of 3 on s squared plus 3 squared, right? Good. And we know that for Laplace inverse, we are converting a function of this form back to this form. So we have sine 80. What we need here is the value for our a and to look out whether there was a constant or there is a constant or not. And now we found out there is a constant and we know the value for a, which is a here, which is 3. You see that? 3. So now let's go ahead and bring sine 80. So sine 80, and we know the value for a 3t. There is a constant, so just bring the constant. Good to go. Once you are able to, if you are conversant with this method, you can just look at the problem and find your constant and just go your way. Because looking at this place is 1, and you found your true numerator to be 3. It means if you multiply 3 by 1 on 3, it's going to cancel your 3 out to give you 1. 1 on 3, right? Find the inverse Laplace transform of this. So, well, looking at this problem, if you have a problem where there is a term multiplying the s component, make sure you factor that out. So in factorizing this out, you see that you can write this as 3 to bracket s minus 1, right? But if you factor everything out, when you multiply or you simplify it again, you should get what was there. What you factorize. So 3 by s will give me 3s root, and 3 by minus 1 is giving me minus 3. In this case, this place is not supposed to be minus 3. So I'm supposed to divide this side by 3 so that if you multiply 2, we get the same thing here. So 5, and don't forget it is a Laplace inverse, right? And I can further factor this 5 on 3 out, right? So 3 to the power, Laplace inverse of 5 on 3. Now this place remains 1, right? 1 over s minus 1. So looking at this, can I do denominator analysis again? Well, it turns out to be like this question is the simplest question, right? So I have to look at where this problem is coming from, because this is what I'm going to take Laplace inverse of. This is just a constant, and the constant, I can just bring it out here. Laplace inverse of 1 over s minus 1, right? So looking for the basic or the elementary Laplace transform, I could see that this is an e to the power at function, which equal 1 over s minus a, right? So there is a need to know the basic elementary Laplace transforms, right? So in this case, I want to convert a function of this form back to this form. What I need is just my a, and there was a constant too, right? There is a constant, right? The constant is still there, so English. So I need the value for my a, and comparing this to that, you could see that my a equal 1. If this place is plus, it means my a is minus, right? But here is the case minus, then my a is just 1. So I can just go ahead and say, oh, turning this back to this is e to the power 80, and now my a is 1. Is there a need to write it? No, just write t. But I have a constant, right? So just bring that constant here. Good to go. So that's it for this question. The Laplace inverse of 5 over 3s minus 1. So once you see the the coefficient of s is not 1, just try to factor that out, and that will make the problem easier. So this will, after you are done, for a constant, no problem. You've gotten this, you have found the Laplace transform, the Laplace inverse Laplace transform, and now comparing this to where it is coming from, we found out that it is e to the power at function. Then just go ahead and look for a value of a, then we are good to go. We know our constant already, just multiply what we get by the constant. So we have to find the Laplace inverse of 7s over s squared plus 4. So first of all, let's look at where our problem is coming from. Well, looking at this problem very well, you could see that it is a cos function. And is it a cos h function, cos h at function, or cos at function? Well, the denominator will tell you, since it is plus, it is cos at function. These are basic elementary Laplace transform, cos at function, right? Good. Since the denominator is positive. So we are able to figure that out, right? So now we know that it is a cos at function, which equals s over s squared plus a squared. Now let's compare our problem, this general formula, to the problem given to us. So we are now going to analyze the question very well. So let's do denominator analysis. When we are done with the numerator analysis. Well, before that, can we factor something out? Yes. We can factor something out. 7 right here, we can bring it here, right? It is a constant. But if we don't want to do that, we don't want to just guess that way, we can still find a way of doing that. Let's go. So let's work with our denominator first. So I'm analyzing my denominator. All right. Analyzing my denominator. This denominator can also be written as s squared plus 2 squared, right? That is okay. Now I'm done. Let me analyze my numerator. So my numerator is supposed to be only s, right? By now it is 7s. You could just see straightforward that there was a constant which is 7. But assuming we don't know, we don't want to just guess it in that form. So it means that something was multiplied by my 2 numerator to give me a fake numerator, right? So we are done with denominator analysis. We are now analyzing our numerator. So something, let me call that thing y, by my true numerator gives me a fake denominator, which is 7s. So now I'm solving for that thing else, and this is equal to 7. This means I have a constant 7, right? So the Laplace inverse of 7s over s squared plus 4 equal to Laplace inverse, I have a constant, so write that constant, of s over s squared plus 2 to the power 2, right? And my interest, since I'm converting a function of this form to this form, my interest to find a and to see whether there is a constant. And indeed there is a constant. And now that I know the value for a equals 2, and it is a cos function, cos at function, then cos at, and my a is what? 2. And then now I'll bring in my constant. That's it. Let's take our final 2 examples. Well, we have to find the Laplace inverse of 4s over s squared minus 16. Now, where is our problem coming from? What formula? Equivalent, this. So now you can see there is s at the numerator side. So this is clearly going to be a cos function. And is it a cos AT or cos cos HAT? For cos function, we have S at the numerator, right? If it were to be sine, then we will not be having S, right? Well, the denominator will tell us that there is a minus sign here, indicating that it is cos HAT. You have to be very careful as when it comes to analyzing this, else you might choose a wrong answer, right? Yes, so it is cos HAT function. And what does cos HAT function looks like? Is just like cos, oh, I'm okay again. So cos HAT equal S over S squared minus A squared. So now let's analyze our problem, our denominator and our numerator. Now that we see where the problem is coming from. So it means that I'm analyzing my denominator. My denominator can be written as S squared minus 4 squared. Since 4 squared gives me 16, right? Here clearly I'm seeing the value for my A, right? Good. We are done with the denominator analysis. Let's look at the numerator. And for cos, my numerator is supposed to be S. By comparing this to the problem given, I have 4S. You could see that clearly there is a constant which is 4. You can just bring it out, just multiply by that. But if you don't want to guess it that manner, let's say if something was multiplied by my true numerator to give me a fake numerator, right? So my true numerator, let's call that thing Y. Multiplying by my S, true numerator, gives me a fake denominator for S. I'm just saying fake because I just want to make it simple for understanding. So dividing through by S, you see your Y is going to be 4. You can see that there is a constant which is 4. You can just factor that out and go your way. So now I'm done analyzing my denominator and my numerator and I found a constant. Let's go ahead and finish what we started, right? So the Laplace inverse of 4s s squared minus 16 so give me, it will be the same as Laplace inverse my constant 4 s over s squared minus 4 squared. And as usual, the Laplace inverse is converting a formula, a term from this form to this form. And we found out it is cos HAT function. So cos H. And I found the value for A to be 4, right? 4t. And now don't forget that we have a constant here. And just bring that constant here. We are done for this problem. Let's look at our final problem. Find the Laplace inverse of 3 over s squared minus 7. So now, where is our problem coming from, right? We don't have s at the numerator side. And this is clearly a sine function, right? And is it sine h, at, or sine at? We are having minus at the denominator side. And this will tell us that it is sine hat, right? Minus sine here plus 80 h80, right? Good. Let's go. So we know that it is a sine function, right? And it is sine hat function, which is a over s squared minus a squared. So now let's analyze our problem. Denominator first. Today, confusion between denominator and numerator. All right. I don't know. So now it means that our denominator is supposed to be s squared, right? Minus a squared. And this is a case that we are having 7 here, right? So what squared will give us 7? You could see that if we have square root of 7 squared, it will give us, it gives us 7, right? So that is how it is. Once you see the value here to be an odd number, your mind will come on things like this, right? For problems of this sort, problems that do not contain shift problem, right? We'll be dealing with shift problems later, and you get to see that they are different thing altogether. Like there is a bit different. So that's it for our denominator. And now you can clearly see that our a here is square root of 7, right? Good. So let's look at our numerator. So our numerator is supposed to be what? Square root of what? 7. Hmm? Is that not true? Yes, that is our true numerator is supposed to be. I mean, true a value is square root of 7. So now let's compare it to our fake numerator, I, like how I call it. Mind you, I'm the one who is calling it that way. So it means that something was multiplied by root 7 to give us a fake numerator, right? So let's call that thing y multiplied by our true denominator, true numerator, to give us our fake numerator, right? Which is 3. So let's divide through by root 7. It's square root of 7. There you see that y is clearly 3 on square root of 7. This becomes our constant. We are done with our numerator analysis and denominator analysis, and we found a constant, which is 3 over square root of 7. So now let's go ahead and evaluate our problem. So the inverse Laplace transform for 3 s squared minus 7 could be also written as, we found our constant, right? Just bring the constant. Mind, this constant can be written before the inverse Laplace transform symbol because it is a constant, no wahala. So over square root of 7 all on s squared minus square root of 7 all squared. So our interest here is to know the value for a and to see whether there was a constant. So since we are converting something like this into this form, let's go ahead, and we know that it is a sine h function. Sine h what? And our value for a is what? Square root of 7. Square root of 7 t, and we had a constant which is 3 on square root of 7. So that's it for this problem. Thank you for watching, and see you in my next video for the shift problems. I mean problems that involve shift theorem.